Hello friends, students. This is Narsimha Rajay presenting Pythagoras Theorem. By prepared show of papers on the theorem, just like the slideshow, it is paper show technique. Let's take a look at the statement of the theorem. Let's understand the very statement of Pythagoras theorem. See, in a right-angled triangle, a square on the hypotenuse is equal to the sum of the squares on the other two sides. In the statement, we read that the square on the hypotenuse, can't it be square of hypotenuse? And it further reads is equal to the sum of the squares on the other two sides. See, squares on the other two sides. Why not squares of the other two sides? So this is because it's not a algebraic square, it is a geometric square. See, here is a right angled triangle. The statement reads that the square on the hypotenuse, see, this is the square that is drawn on hypotenuse, see, having the length of all the four sides equal to the hypotenuse. See, this is what the statement means. And further, this is equal to, see, this is equal to the area of this square is equal to the sum of the areas of the squares that can be drawn in a similar manner on the other two sides. Say for instance here the other two sides are AB. See, equal to the length AB. See, here we have drawn, taking that length, a square. Its area is a side square, AB square. Here is taking BC. It means on BC itself, taking that length, all four sides, the area of this square is side square, BC square. So Pythagoras statement basically reads this one. The square on the hypotenuse, meaning the area of the square that is drawn on hypotenuse, is equal to the sum of the areas of squares. See, squares meaning areas of squares that are drawn on the other two sides. See, on AB and on BC, whatever the squares that are drawn, the areas to be taken, the areas to be computed, AB square, BC square, then we have to add them. So this is basic statement of Pythagoras theorem. Let's proceed to write what is given by reading the statement. See, if you read the statement of the theorem, see, statement gives us a right angled triangle and further things are asked to prove. So I will take a right angled triangle with name ABC and will highlight as to which angle is right angle. See, at B it is right angle. So angle ABC is equal to 90 degrees. Further, let's proceed to write what is needed to be proven. So what to prove? So from the statement we read that the square on the hypotenuse, see, it is AC square, is equal to the sum of the squares on other two sides. See, sum of the squares on other two sides. See, it is AB square plus BC square, meaning areas of the squares to be added to be able to equal to the area of square that is drawn on hypotenuse. So AB square plus BC square will equal the area of square drawn on hypotenuse, AC square. So this is required proof of the theorem. AC square is equal to AB square plus BC square. See, the proof of this Pythagoras theorem is offered based on the knowledge of similar triangles. So in order to create two or more Similar meaning already we had started with a right angled triangle. So 2 or 3 right angled triangles are needed. So the reasonable construction is to have a perpendicular drawn in the right angle from the vertex that is already having a right angle at it. So BD perpendicular dropped on AC is most suggested construction. So BD perpendicular to AC. By this we will have created a right angled triangle. See here BDC and another right angled triangle ABD. See here is right angle and already we have our right angled triangle ABC. So total 3 right angled triangles are here after the construction BD perpendicular dropped on AC. See, in the proof, we shall consider the bigger triangle ABC and in among the 2 smaller newly created triangles, one, say ABD in the first instance and that BDC will be taken in the second instance. So consider the triangles ABC and triangle ABD. See here it is filled in yellow color. See in the proof we will try to prove that these 2 triangles are equiangular by establishing 3 pairs of equal angles and then we will announce that they are equiangular and then we will write that the triangles are similar, then their corresponding sides are proportional and we will proceed to get the required get at least near to the required proof. So let's begin our discussion. See the first pair we will write the angles that are equal to 90 degrees in these 2 triangles. Angle ABC is here, angle ABC 90 degrees. Angle ADB, angle ADB 90 degrees. See these 2 are equal to 90 degrees. Because one is given to us. See about this angle B which is 90 degrees. We had started with a right angled triangle. Remember that it is given to us. And second one is we had it in construction. We had dropped BD perpendicular on AC. So when we dropped perpendicular, see here it became right angle 90 degrees. Second pair, angle BAC equal to angle BAD. Angle BAC, angle BAC, see this angle and angle BA, see we are stopping at D, BAD, BAD, so this angle, see these 2 are one and the same, whether you name it as BA and go up to C and name it as BA and stop at D, they are one and the same. So we write them as common angle. You may notice here common angle, not angles. It is common angle. It comes in both the triangles. So this way second pair is established. Now it's time we move to third pair. So it is angle ACB, angle ACB. See we had not used this angle so far. And in the smaller triangle angle ABD, angle ABD. See this portion of the right angle that goes into this triangle. So this is not used. So these 2 remaining angles must have to be equal because already 2 pairs have been established as equal with valid reasons. So third pair has to be equal. Now we announce that the triangles ABC and ABD are equiangular because all the 3 pairs are established as equal. Now we further say that when the triangles are equiangular, they are similar. Then corresponding sides are proportional. Yes, corresponding sides are proportional. So let's write the corresponding sides in ratios and write that the ratios are equal. So equality of ratios is proportionality. So we have to do that. First pair AC by AB is written by making use of this pair of angles that are equal to 90 degrees by writing the sides that are opposite to these two angles. In the bigger triangle, angle ABC 90 degrees, opposite of that is this side AC. So AC is written. And in this smaller triangle ABD, it is here the 90 degrees. This is not the 90 degrees. The full angle B, ABC belonging to bigger triangle is 90 degrees. Actual 90 degrees, complete 90 degrees that belongs to ABD triangle is here. Opposite of 90 degrees angle is here AB. So below AC we have AB. So 90 degrees angle in the bigger triangle B, opposite of that is AC, and here is 90 degrees in smaller triangle, opposite of that is AB. So AC and AB, so they are in a ratio. Now common angle A used in the second pair. So opposite of A in the bigger triangle is BC. Opposite of A in the smaller triangle is BD. So here it is opposite of angle A, BC, and here it is opposite of the same common angle BD. So BC by BD. So this is second pair. Now moving on to what we have written in the remaining angles. Angle ACB. Angle ACB, opposite of this angle is AB. Remember this? AB. And here it is ABD. Want to look back? See, here is ABD. ABD, opposite of this angle is AD. So here it was AB and here it was AD. So AB by AD. So like this we write three pairs of ratios of corresponding sides. We do not want BD to be in our calculation because BD is our construction and it is nowhere required in the proof that we have calculated already. So we exclude this term of ratio and connect first and last. So AC by AB, this one, and we write is equal to AB by AD. AC and AD cross multiplied, see it is AC into AD. AB is multiplied, it is AB square. See, this is how we arrive at note 1. Let's continue the proof by taking this time triangle ABC, keeping the big triangle same once again, and this time changing the smaller newly created triangle. Earlier we had selected ABD, now we have gone for BDC or BCD. So consider triangle ABC and triangle BDC. See, the same discussion is carried compared to previous section. First we will try to prove that the triangles are equiangular, then they are similar, then we proceed to write the corresponding sides as proportional. So remember what we had done earlier? We had written the angles that are equal to 90 degrees. So in the big triangle, it is angle ABC that is equal to 90 degrees. So angle ABC, and here it is BDC that is 90 degrees. So BDC. One is given. About this bigger triangle, we people were given in the statement of the theorem, and second one we had it in construction. This suppose BDC. See, this BDC became 90 degrees when we had dropped BD perpendicular on AC. Moving on to second one. Remember the second pair that we had established in the previous section? We had gone for common angle. Yes, we will be doing same here. BCA angle C. BC, we will stop here, D. Angle C. See, angle C is common here in bigger triangle as well as in smaller triangle. So common angle is noted. Now the remaining angles have to be equal because two pairs of angles from these two triangles are proved as equal with valid reasons. So third pair has no reason to escape, that has to be equal. So BAC, that we had not used, so that angle, and here CBD, see this portion of right angle, this is right angle, no? ABC, right angle from the original big triangle. CBD, see this portion, CBD is equal to BAC. So BAC angle of this big triangle equal to CBD angle of the smaller triangle, because they are remaining angles. So in this manner we announce that the triangles are equiangular, triangle ABC and triangle BDC are equiangular, therefore they are similar. Then corresponding sides are proportional. So let's proceed to write the ratios of corresponding sides as equal. Let's see. Let's make use of the angles that are equal because they are equal to 90 degrees. Here is the angle that is 90 degrees in bigger triangle, angle ABC. So opposite of that we have a side A to C, AC. So here is AC. 90 degrees is here, angle BDC in smaller triangle. Opposite of that one is here BC. So below is BC, AC by BC, one pair. Let's make use of common angle C that comes in both the triangles. Opposite of C here is AB. See this side AB. Opposite of angle C is here BD. So here it is AB, here it is BD. So AB by BD, second pair. In a similar manner, let's make use of these two angles that we have written under remaining angles that are equal. Angle BAC, see this angle, opposite of this angle is BC. See this BC, remember this BC. Now CBD, see this portion of the angle, opposite of this is DC. So BC by DC. So in this manner we write three pairs of corresponding sides in ratios. One pair of corresponding sides in ratio, second pair, third pair, and we write that they are equal. See, this is what we mean by saying corresponding sides are proportional. Exclude this middle term of ratio because it has BD. See, BD we don't want in the final proof, it will not come there, we have calculated. So BD to be excluded. Omit this term of ratio AB by BD. Connect first and last. So AC by BC, BC by DC. AC and DC multiplied, see, cross multiply them, AC into DC. BC is multiplied, so it is BC square. So this is how we note 2. Now let's add 1 and 2. See, here we have listed 1 and 2. Equation 1, note 1, equation 2, note 2. They have been written. We are adding AC into AD plus AC into DC is equal to, on right side we have AB square and BC square. See, they are added. In these two terms AC is common, let's write it outside, and in brackets AD plus DC. See, AD and DC can be added by looking at triangle. Take a look at the triangle. See, here is AD and here is DC. So when you add AD to DC, you get the length of a full side AC. So here is AD and DC added, that gives AC is written. So AC into AC, AC square, the right side is following AB square plus BC square. So here it is. So AC square is equal to AB square plus BC square. So this is the required proof of Pythagoras theorem. Thank you for watching this video.